Hello and welcome. My name is Mark Horseman, Data Evangelist with DataVersity. We would like to thank you for joining the latest installment of the monthly webinar series, Analytics Architecture with William McKnight. Today, William will be discussing Edge Computing Evolved, introducing the zero DBA, zero ETL embedded database. Just a couple of points to get us started. Due to the large number of people that attend these sessions, you will be muted during the webinar. For questions, we will be collecting them by the Q&A section. If you would like to chat with us or chat with each other, we certainly encourage you to do so. And just to note, the Zoom chat defaults to send to just the panelists, but you may absolutely switch that to network with everyone. To find and open both the Q&A and the chat panel, you'll find the icons for those features in the bottom middle of your screen. As always, we will send a follow-up email within a couple of business days containing links to the slides, a recording of this session, and any additional information requested throughout the webinar. Now, let me introduce to you our speaker for this series, William McKnight. William has advised many of the world's best-known organizations. His strategy formed the information management plan for leading companies in numerous industries. He is a prolific author and popular keynote speaker and trainer. He has performed dozens of benchmarks on leading database, data lake, streaming, and data integration products. William is the #1 global influencer in data warehousing and master data management, and he leads McKnight Consulting Group, which has twice placed on the Incorporated 5,000 list. And with that, I will hand the floor over to my friend William to get today's webinar started. Hello and welcome.
Hello, Mark. Hello, everyone. Welcome, everyone. Coming to you today from my home in Plano, Texas. I see somebody chatted that they were in Dallas. We're practically neighbors, Marina. What is going on? I've been collecting some headlines for us just to show you that what we do in the world of data has high impact and it's making a difference out there. You might say for better or for worse as I go through this, but NVIDIA became the first company to reach 4 trillion. I believe that was last week. An AI-generated band on Spotify has over 1.1 million monthly listeners with 2 albums released last month. AI-generated band. Amazon has deployed their 1 millionth robot. And YouTube is going to crack down on all those videos that are fully reliant upon AI. Now, I watch a lot of YouTube and I can spot an AI video now, and it just sort of rubs me wrong that it's all AI. Sometimes the content's still good, but I still don't know that I like that fully. So I'm glad they're cracking down. We'll see what happens with all that. Now, today's topic is edge computing, and it's a topic that I find that there's going to be a whole lot more interest in the topic from certain industries and maybe a little bit less from other industries. But there are quite a few industries that are interested in this topic, including healthcare, manufacturing, retail, autonomous vehicles, entertainment, smart cities and urban development, banking and finance, supply chain management, anybody that has a supply chain, that is, gaming, and smart homes, and probably quite a few others that I'm not thinking of. But if you have edge devices and you want to do some computing there, then you're into this world, and the decision points just go up exponentially in this world from outside of the world, I guess I would say. So we're going to break it down for you here today so that you have something to go on as a data professional in this world. I am advocating the use of databases out at the edge, of course, and suggesting that they may be zero DBA, zero ETL, and in the embedded form of a database. So I'll break that all down as we go along here. These are some of the logos we're associated with in terms of tech expertise. Yes.
William, I've still got the slides on my screen. So if you're flipping through slides, we're not seeing it.
Oh, really?
Yeah.
Okay.
You want to grab the share real quick?
I am trying to flip through slides. Let me see. What have I done wrong? Okay.
You just got to take the share back. Yeah. Sorry, buddy.
Now.
Yep. I see your presentation mode.
Okay.
There we go. That looks great. Yeah.
Wow, that's different. We got it on a different screen today. Oh, that's perfectly fine though. Okay, I think my finger jumped on the clicky. Okay, anyway, these are some of the slides we're associated with. Happy to talk to you about any of them or all of them. The decision points go up exponentially as you are talking about multiple of these, as most of you are. And so that's a true architecture in an enterprise. We love to talk about that stuff. Now, one thing driving edge computing is the proliferation of IoT devices. And as you can see from this chart from IHS, the growth of IoT connected devices, it's just fueling the market because they generate massive amounts of data. And these devices require real-time processing, and they transmit this data to centralized cloud or data centers, which can be challenging due to all the constraints that we'll go through that are out there in the edge devices, bandwidth constraints and latency issues. Edge computing enables data processing closer to the source. That's the good news. And it reduces latency and optimizes bandwidth. However, there are several big decision points to be made in an edge computing environment, not the least of which is, what are we going to put at the edge? How much processing, how much storage are we going to put at the edge? What data exactly do we need out there to do the things that we want to do? The more data, the more analytics you can do. The less data, the less of an expensive device that you need, and probably the less data movement that you have to make back to a centralized device. It kind of boils down to that, but that's a mouthful. And that's a lot of work right there, a lot of great decision points that you get to make. The good news is that whatever you're thinking about is probably possible today, because one thing I hope to do today is kind of open up your eyes to all the possibilities that are possible now with edge computing that really weren't possible even up to a couple of years ago. And a lot of it's because of the databases that we could put out there at the edge. So I really want to get focused on that as we go along here. But a little bit of background. What is the edge? The edge is where things are, okay? So if you're a connected car, it's the car, okay? If you're doing toll booth processing, it's the toll booth reader, okay? It's wherever things are, wherever you have those readers, those Raspberry Pi devices or whatever devices that you have out there at the edge. It's where highly available processors enable real-time analytics for applications that can't wait a long time for decisions. And this is because there are constraints, limited processing power, limited storage, and limited power, period. These edge devices, they might be battery powered, or they might have power constraints. And this is all due to factors mainly has to do with size. Size constraints, of course, power consumption, cost considerations as you proliferate the devices, and real-time processing requirements. Edge computing focuses on processing data in real time using available resources efficiently. And there's 100 ways to skin that cat in your architecture. So let's move into some of the decision points as we go along here. Now, we are going to talk today mostly about the edge database because I speak to the data professional. However, the other and possibly more exciting part of this is edge computing. What can you do? What can you do with all that data out there? Distributed computing that processes and stores data at the edge of the network. So today, again, databases, but there's a lot going on out there in terms of processing, including today we have AI. And AI is made more possible out at the edge because of special chips that are made by Google. They call theirs Edge TPU, Intel, Movidius, Myriad X, I believe they call theirs. NVIDIA has one, Qualcomm, Intel's is Neural Stick. And these are designed to provide low power consumption, high performance, and efficiency for AI processing at the edge. How exciting. So we can do more than just really basic transactions now at the edge. So let's open up our creativity when we're talking about a network like this. These chips optimize AI workloads, delivering fast inference and processing while minimizing power usage. Yes, inference at the edge is possible now. Edge computing is a distributed computing paradigm. It brings data processing and storage physically closer to the source of data generation. So that data intake is very important. The data writing is very important in the edge. Now, these edge devices, they can be Raspberry Pi. We have a lot of experience with that. And in the graphic, you see somebody holding a Raspberry Pi. That's a lot bigger than a lot of them, actually. But that's a Raspberry Pi device. You can have IoT sensors, smart cameras. So at the edge, you can certainly be taking in imagery, edge gateways. You can have various devices in autonomous vehicles, and so on. Now, edge devices collect a wide range of data. Now, I often have thought, well, what kind of data can that actually collect? Now, you can infer that, okay, it's going to pick up temperature, humidity, pressure, and vibration. Okay, stuff like that. But if it's a camera, it can also pick up video and image data from smart cameras. They can collect data from industrial equipment, like machinery performance and production metrics, and environmental data, such as air quality and noise levels. So there's a wide range of interesting data that can be collected. Now, one of the interesting data points or architectural points in this is, what do we really need to store, and how much of it do we need to store? And this gets into the time series data that's usually involved in edge devices, and we'll get into that. But how many generations of that data do you need? If you're in an autonomous vehicle and it sees a stop sign or it sees a red light, it just acts accordingly, right? Do you need to store that information? How long do you need to store that information for? Do you need to send that back to the cloud for long time storage keeping? I don't know. Some of it you do, some of it you don't. Therein lies why I say that there are exponential decision points when you are talking about edge architecture. Use cases. Great way to start the topic, I believe, is to talk about some of the ways that this can be used. Airlines power in-flight seatback apps without relying on internet connectivity. Retail, enabling digital kiosks for customers to look up items or make purchases. I think we've all seen these on some of the tabletops out there. Restaurants, supporting digital tabletop ordering systems. Okay, so it's retail and restaurants that have these tabletop type kiosks. Event venues powering digital ticket turnstiles, mobile airline apps, and all kinds of apps where you have full features online. For an airline, for example, you can check in, get your boarding pass, all this sort of thing. And socially connected mobile games. So you want to be able to play the game, whether you're online or offline. And another big decision point is, well, how much are you going to allow somebody to continue to do if the game goes offline? And does the game go offline normally? So all of that. And when you come back online, you got to get back to current state, right? So updating your game position and recording new achievements locally and pushing the latest achievements and game status to the back end, because that's information that's collected over the long haul. Now, do you want to bring some of that information to bear out at the edge? Remember, all the data for the user doesn't have to come from the edge. It's just that quick data that you want on the edge. You can also have, as an example, aggregated IoT sensor data from anything that could throw off sensor type of information. And you want to copy that data to your backend database when you get online or on a regular basis or in real time. And so I'll give you some metrics as we go along here to speak to the viability of your architecture. Because we have actually benchmarked edge computing. And we've done extensive work as industry analysts in the space. So a lot of that is embedded in here today. Edge computing offers several significant benefits, primarily driven by its proximity to data sources. Low latency, which processes the data closer to its origin, leading to faster response times. And that's critical for applications that require real-time decision-making. Enhanced security by keeping sensitive data local and not copying that data to a backend database. Reduces the risk of exposure as less data needs to traverse the public network. Improved bandwidth efficiency, so local processing minimizes the amount of data transmitted to the cloud. Again, I was saying earlier, do you have to send all that data to the cloud? Do you have to send all that data to a database for longer term storage? Probably not. Probably not, because this is data that just gets generated and comes and goes, but it's useful to the processing of the real-time operation. This is all going to conserve network bandwidth, especially in environments with limited connectivity. And you also have to have offline operations, so edge environments can enable functionality even during network disruptions. How much functionality? Well, that's a big decision point. So I'm going to say here that edge computing increases your architectural decisions by 2 to 3x. 2 to 3x. So if you're used to building analytic architectures, different forms of information architectures, okay, let's add in the edge. You've got that many more decisions to make. And that's okay. We'll make them, but just keep that in mind. You might have to allow for a little more time than what you may think because of all of these decision points. So there's no DBA in these databases that we're going to put out there. Embedding a database means integrating a DBMS directly into an application, which allows the application to store, manage, and retrieve data locally without requiring a separate database server. Whereas in the past, what we're mostly used to, embedded systems, was something of a black art, requiring in-depth knowledge of electronics, oscilloscopes, and other fun stuff like that, interrupt processing, internal hardware architecture elements and assemblers, protocols, and hardware-assisted debugging, none of which I'm an expert at, so I'm glad it's easier for me. This is the area where it tends to really matter in embedded databases is write speed. I mentioned that before, write speed. This is the essential performance metric for IoT data. Now, I said I'd give you some things to think about when you select that database. All right, so you can test your database with synchronization, so it's constantly talking to the cloud database, and you can test it without. And both performances are probably important to the overall architecture. So without, you want to look at things like inserts and queries of, I'll put a number out there for a medium-high size implementation, 10,000 documents on an index key. Queries of 5,000 documents on a non-index key. So you can index or not index your keys, right? Deletes of 10,000 documents on an index key and deletes of 5,000 documents on a non-index key. Updates on the index key and non-index key updates. Okay, so there's some metrics you want to look at when you're testing out your architectural pieces, including the, of course, database out there. And then test all that I just said with synchronization back to the server. And see how it goes. Make sure the performance is going to be adequate for the need. The solution needs to automatically synchronize in real time between that remote device and a server without ETL. So how does it do it without ETL? It does it with things like message queuing and APIs, right? Not ETL. This capability is critical for today's needs and uses because the potential number of mobile devices could easily number in the tens of thousands for a given application. And all that information may need to funnel into that core database that's on the server. So now, how many edge devices are you going to have in your architecture? Is it tens of thousands? Probably not. Frankly, I haven't worked on one that big. Mostly, I've been in the thousands. Okay, that's where you mostly are in terms of edge architectures, but sometimes hundreds. And you know what? This also works if we're talking down in the dozens. It's still an edge architecture, and it's still viable to do, even down at that lower level number of edge devices. And usually, the number of edge devices is pretty dictated by the operation. You know, you have a driverless car out there, okay, however many cars you have, that's your edge. You have toll booths, that's your edge, right? But sometimes there's some variability in terms of what you want to make an edge. I won't get into all that, but usually the number of edge devices is pretty dictated by just looking at the business. You put these embedded devices at the edge, and there are, realistically, there are other types of databases that you could use in an environment like this. Distributed databases like a Cassandra, DynamoDB, and MongoDB. And by the way, as I classify these databases can be classified in different ways. I'm doing it my way. They may have a different way. Somebody else may have a different way, and that's okay. But there are distributed databases that are designed for local storage, whereas, embedded databases are designed for local storage. Distributed databases are designed for large-scale distributed systems, and in my opinion, not appropriate at the edge. There's in-memory databases. Embedded databases store data on disk or in memory, but in-memory databases store data only in memory. Now, you can decide if that's right for you. You've got your Redis, times 10, databases like that can be at the edge. And then there's mobile databases like SQLite, Couchbase Lite, databases like that can be used in mobile applications. But mobile databases often have specific features for mobile devices. And oftentimes at the edge, it's not a mobile device. It's not a phone. It's not a mobile device like that. And mobile databases focus on supporting mobile application user mobility, whereas embedded databases focus on providing high performance data management within a larger application, which is more what we're looking at. So these mobile databases, just to expand on this, because people ask, these are example variations for a given mobile database that's out there on the market, one of the leading ones, which we used to use for our edge architectures. Mobile databases prioritize offline functionality and local data storage, sacrificing some advanced features that are found in traditional databases. They often lack or limit features like sharding replication, advanced security configurations, and server-side scripting. This trade-off enables mobile databases to provide fast, reliable data management on resource-constrained devices, yes, but there's so many more benefits from an embedded database. So quickly thinking through this one particular mobile database, it uses SQLite as a simple key value store behind the scenes due to its stability and prevalence on devices. And as such, the mobile database does not provide the ability to configure the underlying SQLite deployment, which a bit irritating. In the mobile database authentication is disabled because the database is designed to only accept connections from within the application itself. This means that the database trusts the application and doesn't require additional authentication for these internal connections. And my security people tell me that's not enough for an edge architecture like this. So the mobile database approach can be considered inadequate for several reasons: the security risk, lack of granular control, an increased risk of data breaches, and insufficient protection. So a lot of it comes down to that sort of thing. Now, so back to why we choose an embedded database. In the realm of edge computing, embedded databases play a critical role in enabling devices to monitor and analyze time series data. And I'll come to that, produced by real-time sensors. By leveraging an embedded database, developers can create applications that efficiently store and process data at the edge, reducing latency and improving overall system performance. So with an edge databases, hopefully high performance analytical stream processing capabilities, embedded applications can then filter, aggregate, and connect collections of time series data in real time and do all the things you see here. Now, synchronization, back to the server, a very fun part of the architecture development. When will you synchronize data? What data will you synchronize? Is it going to be two-way or one-way? Because it can be one-way, and that's called push synchronization. So I'm advocating bidirectional. I'm advocating setting it up that way because eventually I think you'll need it if you don't initially. And most of us can think of things we want to do bidirectionally initially anyway. So, for example, industrial sensors collect data locally using something like a SQLite and sync periodically with a cloud database. Effective data synchronization is paramount in edge computing to maintain data consistency between the edge nodes and the central cloud. And there's these two common patterns: bidirectional, which is shown on the screen, and there's also the push only, where edge devices just push data to a central cloud repository. So oftentimes you want to push the data from the edge into the central cloud repository. You want to analyze it with all the other data that's there. Okay, do your analytics. And then those analytics inform the data that is going to be used out at the edge. So you want to be able to push those analytics back out to the edge. In other words, the next time this customer comes in to the store, offer them this. Okay, because this is their pattern. We've updated their pattern in terms of how we want to guide them in the store or the online store, as the case may be. So in comparison to push is that one way. You have limited flexibility, and there's now for both ways, there's also a potential for data overwrite. That's a term you want to be familiar with in edge computing. Data override issues arise when new data overwrites existing data, and this can potentially lead to data loss, inconsistencies, and conflicts. And this can occur in both push and bidirectional, especially when you have multiple devices or sources updating the same data simultaneously. So without proper conflict resolution strategies, which you'll want to add to your architecture time, overwrite can result in unintended data loss or corruption, compromising data integrity. So we won't get into conflict resolution strategies. It's a little too much in the weeds for today, but do know that you'll have to architect around that potential issue. So I've talked a little bit about the constraints out at the edge. Again, here they are: CPU, memory, storage, and power, resource constraints, very small footprint, but not the least of these is connectivity, network connectivity, conflict resolution, data synchronization, which we just talked about. Despite its advantages, implementing databases at the edge presents unique hurdles. Resource constraints. Edge devices typically have limited CPU memory and storage capacity, as well as power consumption limitations. Now, this may go away over time. All right, edge computing may go away over time as cloud computing becomes faster, as we're able to do the processing remotely. Okay, but it's not today, and it's not in the foreseeable future, and it's certainly not in the what I call the architectural future, in terms of what are we architecting for. We are not thinking that way now. Well, I'm saying we, my firm, we're not thinking that way now. We are thinking that the edge lives on and is important, and these databases out at the edge are important. And I do mean databases and not flat files. There's a lot of flat files out there at the edge, not databases. This is the older way to do it. This is the way that I remember doing it maybe a decade ago. This lacks data portability. There's no single API portability across programming languages like NoSQL and SQL. Implementing a custom data storage solution with flat files can lead to all these challenges. And this can result in data integrity issues such as missing or inconsistent data and corruption. Additionally, think about your database. Features like indexing, filtering, SQL support, metadata management, and synchronization need to be built from scratch. Furthermore, security measures, reporting capabilities, auditing, and file management functionality also require extra development effort. I can think of really no edge architecture that I've come across that really is better served by a flat file out there instead of a database, given where databases have come to. So let's talk about taking this a step further now that we have a little foundation in edge, and talk about architecting for the edge. And I've alluded to several of these decision points, like storing data at the edge. Store and forward is a technique in where you temporarily store data locally and forward it to a central database at a given time. Usually it's when you get connected. And sometimes it's on schedule, and sometimes it's just, well, when we reconnect, whenever that is. And really, you have to architect for the whenever that is possibility, because connectivity is not guaranteed 100% between the edge and the cloud. So that's one way. The digital twin is an increasingly interesting way as well, where you create virtual replicas of physical devices which enables simulation, analysis, and optimization. Digital twins can provide a comprehensive view of the entire system or process, integrating data from multiple edge devices and other sources. So I've seen some really great looking digital twins of cities, of factories, of supply chains, etc. Gives you a great visual as to what's going on overall. Time series data at the edge. Yeah, I've alluded to this. I've said, yeah, it's mostly going to be time series data that you collect out there at the edge. It's mostly going to be fast, recurring data. Time series data tracks changes to a system or process over time, with each new measurement recorded as a separate entry. This type of data is characterized by being append-only, time-ordered, so the timestamp is important, and focused on measuring change. Change is what's important here. Is the temperature going up, just consistently going way up and out of bounds? Should we do something about that? Examples include sensor readings, DevOps monitoring data, financial transactions, are they out of whack? And web application event streams. By preserving a history of change, a history, not a complete history, but an architected history, something that you give thought to in terms of how much history do you need? How many generations do you need? It's typical to store a certain number of generations of time series data. It's also typical to store a certain time frame of time series data, the last 5 minutes, the last 10 minutes, the last hour, the last day. Now we're adding up data, probably. Okay, you see how you have to make all these trade-offs. All this data, as much as you can keep, is going to help you enable analysis of past trends, monitoring of current performance, and prediction of future outcomes. And you have to decide, are you sending the data back to the database and incurring that overhead so that the central database can have all this time series data from all these edge devices and do some really good big time analysis? Is that valuable enough to send the data? Or you just want to do localized analytics based upon the time series data that you do collect out there in that particular device? Yes, big time decisions here, fun decisions. The rapid accumulation poses storage and querying challenges, making specialized time series databases increasingly popular for managing and leveraging this valuable data. And there's time series focused databases, and then there's databases with great time series capabilities. And I show you some examples at the edge of time series data. So oil and gas, agricultural mapping, black box equipment, self-driving cars, etc. What you see there. So all these things are interesting from a time series perspective. Now, IoT device differences from traditional data requirements. Not that long ago, systems managed dozens of connected devices. These days, the number of intelligent data collection points or intelligent connected devices can be in the thousands or tens of thousands. As I mentioned, the number of IoT devices can change in real time within a single setup. And you certainly want to set it up that way. You don't want to hard code the number of edge devices in the architecture, right? You want to take them down, add them as needed, and bring them in to the network. Edge nodes' physical connectivity is often unpredictable. This is due to various media and bandwidth availability, the wide range of protocol stacks over which the devices are connected, Wi-Fi, Ethernet, cellular, as well as specialized stacks. Okay, sometimes edge device connectivity is intermittent because of the physical device locations, or they're battery operated and the batteries die or something, and only phone home periodically to maximize battery life. So we're maintaining battery life by having less connectivity. Another big decision point. Fun stuff. Okay, now this is an example of an airport, and there is you got the terminal, you got your airfields, and various things here that you can see show all of the various edge computing that actually happens in an airport. Now, I know we don't all work at the airport, but we all use the airport. So I figured it was something we could actually know something about and relate to. But we all in edge computing have something like this, maybe not as complex, but you've got, I'll quickly go through this. Now you've got your terminal presence. This diagram shows how a terminal uses Wi-Fi access points and microcells to connect passengers, surveillance systems, biometric identification, and motion tracking. This network infrastructure supports communication, security, and operations within the terminal. And then airfield premise is the area outside the terminal where various components are digitally connected. These include the connected aircraft, likely involving telemetry and ground communications, vehicles like baggage, fuel trucks, surveillance systems, security and monitoring cameras, and the workers who may have tags, who may use mobile devices or wearables for coordination and safety. The connectivity backbone for this environment is powered by microcell or macrocell towers, which deliver cellular coverage across wide open airfield areas. So they're all connected out there by cell towers. The double red stars, you can see the double red stars in there, suggest the importance or strength of this cellular infrastructure. And then moving on, we've got the airport multi-access edge computing, which brings cloud computing capabilities to the edge of the network, processing data closer to where it's generated and enabling real-time applications. Very important there. And I'm showing off Actian Zen as a database that checks all the boxes that I'm talking about here today. It's one we're very familiar with, and it's central to some airport operations. So these databases are central to edge computing environments. And finally, the airport VPC, or the virtual private cloud, it comprises multiple layers that you see there. Quickly, though, the top layer features applications such as airport management, airlines management, and business support systems. The middle layer includes network services. The infrastructure layer consists of the virtual WAN, etc. things. Additionally, Azure IMS is integrated into the infrastructure, which enables telecommunications service providers to deliver multimedia services such as voice, video, and messaging. So all that's really pretty important in the environment. Now, the edge database supports the connected airport architecture in several ways. I mentioned it's important. It's important for real-time data processing, edge computing, the integration with the Intel MEC, support for airport real-time applications, data management, and scalability and flexibility. Now, this topic, I like to inject some humor into my talks, and this topic just really doesn't lend itself to a lot of humor. It's not very funny. The projects are a lot of fun, but the topic isn't all that funny. So I added my graphic here for a little bit of fun right here at this point in the presentation. So we're all into the agentic AI economy. Down here at the bottom is, please, bro, response in valid JSON format without errors and make sure if the syntax is correct. I'm begging you. Okay, so I thought that was fun. As we move into the agentic AI architecture economy, we'll talk about that some other time. But here's another example. The industrial IoT, Internet of Things architecture. So you got data sources. This section represents the physical components of the system, like the plant and the manufacturing system, communication protocols, which supports communication across multiple protocols, enabling seamless data exchange. The gateway or edge, the gateway edge tier integrates multiple and disparate IT operational tech systems. The platform, which comprises the key components of data transformation, industrial connectivity and device management, and also the visualization. We're not getting into that a lot today, but the visualization of this data can be very interesting as well. And very importantly, the database is there in the platform layer. The edge database is essential for industrial IoT applications that require real-time data processing, decentralized data management, and advanced data analytics. Its importance lies in its ability to improve responsiveness, security, and scalability while reducing latency and bandwidth usage. So these components all work together to provide robust platform capabilities. And finally, you are looking for databases that are purpose-built for edge distributed data. And the next section, I'm going to go through your top 6 criteria that you want to look at for those databases. But first, security. Now, it's not one of the six. It probably should be, or it's number 7, if you will. I'm a data guy. I'm not a security guy, but it's important enough to make sure that it's in here so that we get people in these projects that can make sure that we are protecting communication channels between edge nodes and backend servers in the right way. Backend database servers are normally run behind firewalls and avail themselves of a full network security apparatus. Server security and authentication is overseen by security personnel regulated by strict rules and procedures. In contrast, edge node storage containers are there in the open, often running unattended, and more often than not, have very limited resources without well-established firewall-like security measures. So device security is a critical concern in edge computing, and the database should be designed to address this challenge with a robust data protection shield. Okay, now with that being said, let's select our 0 DBA, 0 ETL embedded database for our edge architecture. And these, I'm getting ahead of myself, but these are the key market needs that I'm going to share with you. We did an extensive analysis on this marketplace recently and came up with these 6 key market need categories. They're not the categories of the basics that we already talked about. Those are there in all of the databases that purport to support this kind of an architecture. But these are some of the ways that databases get set apart from each other in the space. So edge databases are designed to operate effectively in environments with constrained resources and intermittent connectivity. So they're different. They bridge the gap between local and cloud. They're typically lightweight and offer fast data access. So let's look at these categories. Make sure that you look for them in your database. Now you might be thinking, well, I don't need that. I don't need vector processing. As a matter of fact, I'm not even doing vector processing in my non-edge architecture. Well, okay, that may be true today, but I see that many enterprises are moving in a vector direction. Now, I've given a whole presentation in this series on vector databases and how important I think they are and how they work and all that sort of thing, and their utility. And so if you're not using vector today, maybe you should be. Maybe there's utility for it that you are overlooking in your enterprise. But I strongly suggest that this be a part of you thinking about the edge. When it comes to vector processing, databases play a critical role in enabling semantic search and retrieval augmented generation, or RAG, for LLMs. We're looking at key features like support for high-dimensional vectors, similarity search techniques, and distance functions, the big 3 of an LLM. While edge databases shine with their lightweight and embeddable design, providing secure and ACID-compliant environments, they often fall short in native vector-specific similarity functions. I bet you're surprised to see me talking about vector at the edge. Yes, I am, because that is part of opening up your minds to the possibilities at the edge. They're well beyond, perhaps exponentially beyond, if you haven't checked in for a couple of years into this space. I know my eyes just keep getting opened up by the possibilities. So many databases lack this built-in vector compression and comprehensive tooling, requiring manual workarounds for storing and parsing vectors. I'm not going to break down this solution does it, this solution doesn't, all that sort of thing. Don't have time for that today. We've done quite a bit of that though, and know that this is a point of good differentiation in the market. And so is inference on the edge. Edge devices require databases that can enable AI ML inference directly on the device for offline or ultra-low latency operations. Key features include low latency, high throughput, and lightweight design. And when we come to the final section here, we talk about benchmarking, we talk about I'll give you some numbers to look at in your architecture. Yeah, we'll come back to that. Interoperability with popular ML runtimes and inference orchestration and caching are also crucial. Edge databases excel at providing fast, low latency data access without network overhead, making them efficient for rapid ingestion of sensor data and quick retrieval of inference operations. However, they often fall short in running ML models internally with a database engine and lack built-in change feeds or reactive triggers to invoke inference logic automatically. On the plus side, edge databases can cache inference results, reducing the need to rerun models and benefiting power-constrained devices. So there's your criteria number 2 for the modern database you're going to put at the edge. Number 3 is multi-model support. All right, multi-model support. And it's of note to me that I find that a lot of the things that I'm now looking for in my edge database are important enough topics that I've actually given full presentations on that topic for your other databases. That's how hard things have moved into the edge. And I think the edge computing is here to stay for quite a while. So if you've been kind of holding off because you're not sure if edge is what the possibilities are at the edge, you might want to rethink that. And when you're looking at those databases and possibilities, look at multi-model support. When it comes to managing diverse data, a single database's ability to store and manage various data models is crucial. We're looking at key features like native support for different data models, cross-model queries, and flexibility in schema design. While edge databases excel with relational and key value data, they often struggle with native support for JSON functions, graph traversal, and advanced SQL functions. Some databases offer flexible schema designs, but others require workarounds, such as storing JSON as plain text or blobs. In real-world scenarios like IoT and recommendation systems, databases need to manage multiple data types, including sensor metadata, logs, user interactions, and predictions. A challenge for databases with limited native multi-model support. Number 4, moving on here, stream data processing and change data capture. Wow. When it comes to powering data synchronization, event streaming, and microservice messaging, databases need to deliver. We're looking at key features like CDC methods, including replication, trigger-based, and log scraping, as well as support for various CDC event types like insert, update, delete, and schema drift. Native stream processing capabilities, including aggregations and window functions, are also crucial. So yeah, we're kind of in the area of Kafka here, having Kafka integration as well as limited support, maybe for complex event processing and schema drift handling. A real-world use case is real-time alerting, where databases capture live changes and apply business logic and trigger alerts via webhooks or Kafka. And finally, I have for you machine learning capabilities. Now, this might be a little bit of a wish list item for these databases, maybe a future item, if you will, because when it comes to machine learning, databases play a critical role, but some of the key features like model support, including locally stored models, SQL native models, and extensibility via extensions may or may not be found in your edge database today. So this is a little bit of my challenge to the edge computing industry, the edge database industry, to do more in this area because I see the utility of it out there in the enterprise, and it's an area of high demand. We want to do way more at the edge than what we can today. And what we can do today is a lot more than, the past, but still, everything's going machine learning. And to do things in an analytics way or a data analysis way out at the edge just is not going to work when the rest of the enterprise is all on machine learning. So there's my challenge to the industry. Come up on that. And actually, there's the number 6, hybrid transactional and analytical processing. We've heard about these databases, and many databases are pushing hard in this direction, blurring the line between batch and online processing, okay? Blurring the line between OLTP and analytical workloads within a single engine. And the way most of them do it is they store the data 2 ways. They store the data columnar, and they store the data row-wise. And depending upon the operation, they just run the optimizer both ways and figure out which one is best. But your analytical queries are going to usually be best on the columnar, and your operational queries are usually going to be best on the row-oriented. So the key is making sure that you can keep them in sync and keep two ways updated and with good performance. But when it comes to combining transactional and analytical workloads, these databases need to deliver both capabilities. Key features include flexible deployment options, storage modes, and multi-threading optimizations. So while databases excel at supporting concurrent transactional and analytical access, lightweight OLAP-style queries, and excellent multi-thread processing, they often fall short in native columnar or hybrid storage and consistent multi-threading capabilities. Additionally, many databases require workarounds for materialized views and automatic refresh, adding complexity to real-time dashboarding. So this is another area that we see happening quite a bit out there in these databases, but more could be done. And it's an area for you to look at because you may want to do that. Benchmarking embedded databases. My last little section here is about, now that we're convinced we want an embedded database, we know a little bit about the decision points we need to make in our edge architecture. We know there's a lot of them. We know we're going to have edge devices. We know that computing and perhaps ML will happen out there. We know some data will happen out there. We know some synchronization will happen back to the cloud database. And we now want to select our database. So, and by the way, we've done this. So what I'm talking about doing here, we've done it. And if you want that benchmark, just send me an email. I'll direct you right to it. We benchmarked and suggest you benchmark, if you're looking at this, TPCX IoT with a custom TPCX IoT-like benchmark driver developed using Python, referring to a 2018 IEEE ICDE paper by this guy to maintain the spirit of TPCX IoT and ensure a fair, objective apples-to-apples comparison. So we executed it using pairs of AWS EC2 instances. Specifically, the instance type you see there that I bolded, each instance with 16 vCPUs, etc., and the database software for each platform installed on these client-server pairs. Next slide, testing methods. So a custom-built Python application serves as the test driver. We perform 3 operation functions. Here's your big 3. Insert. IoT data inserted into the client database, measuring insert, throughput, and averages. Query and synchronization. Use Python multiprocessing tools to simulate multiple sensors. And blah, blah, blah. You see a lot of the details there. Again, if you want the full details, go ahead and send me an email. I'll be glad to share that with you. And there are, I'll just point out on this, there are specifics, solution-specific methods that almost must be deployed in order to get the data into the database. So, and the measurements, this is probably the more important part of this, right? What are you looking for? Sensor reading throughput measured as IoT records per second, similar to the TPCX IoT's IoTPS metric. So sync latency and the timing and the number of analytical queries. These were not tracked due to the varying ingest rates across platforms, which would create an unfair comparison. Analytical queries were primarily there to add pressure on the systems. The benchmark provides a direct data-driven comparison of these database solutions by simulating a common IoT workload, your workload, and measuring its performance in terms of data ingestion throughput and latency under varying sensor loads. Okay, so in summary, edge computing with a 0 DBA, 0 ETL embedded database is quite possible today. Process data closer to its source to reduce delays and boost performance, understanding that there are limitations, and you select lightweight databases that thrive in resource-limited settings. Implement reliable synchronization strategies to overcome intermittent connectivity challenges, and you'll want a connectivity strategy as well as part of this. leverage edge databases to process data in real time because you're out at the edge while maintaining consistency across distributed systems, not overwriting data. So edge computing, again, edge computing's core benefit is bringing data processing closer to reduce latency and improve performance. The importance of choosing lightweight databases optimized for resource-constrained environments. That is important, in other words. The necessity is implementing robust synchronization strategies to handle intermittent connectivity, and ultimately, edge databases enable real-time processing while maintaining data consistency across the system. Okay, that brings me to the end of the formal part. We've got a few minutes left, Mark, for any questions.
And we've got a great question in here, and it's something that that I've struggled with too. And so it came up early in the presentation, but you kind of came back to it near the end as well. So the questioner said, when integrating data from IoT devices like sensors, how should this data be categorized within the data modeling layers, logical, physical, or otherwise? Specifically, where does raw sensor data fit in the architecture, and how should its metadata be captured, stored, and managed?
Yeah, I mean, it's data like any other data. It's a special kind of data in that it's not third-party data. It's obviously internal data, but it comes from the edge, so it's a little less under control, I'll say, than our internal data that we have full control over, like our ERP data and stuff like that. So what I like to do is bring it into my data lakehouse, and pretty much for me, everything's going to be in a data lakehouse, one or the other, out there on the edge, if you will, if I can use that term, of a data mesh type architecture. That's our ideal architecture that we strive for today. But anyway, bringing it into the data lakehouse and modeling it with a particular naming convention that indicates that this data came from the edge. So that probably implies a certain level of trust that a user or an application can have in that data, which is probably less than maybe some other data, perhaps even more than some other data, like pure straight on third-party data we have zero control over. Okay, this data, we're going to do less data quality processing. We're going to have less data analytics that occur with that data out there at the edge. So for various reasons, it may come in with a little bit less data quality. Now, if we're improving that data quality for purposes of analytics, great, go for it. If you can find the pattern that you want to improve on, and that is something to update at the edge. But updating at the edge is a big deal because you're talking about a lot of edge devices, potentially thousands of edge devices that need that kind of update processing. It's easier to handle things oftentimes at the data level. And so just special naming, I would say, and special consideration.
Yeah, that makes a lot of sense. Like in my past dealing with sensor data coming from trucks, it was real interesting because of the consistency of how sensor data presents itself. Like you could just that's what I did too, William. I just chucked it into a lake. We make that sound easy, don't we?
Well,
We do have
you
another.
have just one more note on that. That
Mhm.
it's very important is you can't count on that data coming in, and while you
Yeah,
might
that's right.
flag the data didn't come in today from such and such truck,
Hmm.
there may be little you can do about it. Life goes on with or without it. So the metadata is pretty important.
Yeah, truck whipping through the mountains, like
Yeah,
you're not necessarily gonna get a signal out there,
right.
even on satellite. We do have one more question coming in. I think it's the last one we have time for. If this can be used for analytics and reporting, how does it take care of data quality issues?
Yeah, you're going to send a limited set of the edge data to the cloud server, which is where we do most of our analytics. You can do some light analytics out at the edge. Uh,
Mhm.
I referred to some of that. So some of the processing around, what you're going to do as next best offer to someone. Hopefully, you have enough data to do stuff like that out the edge, but it's supported by the data that you've brought in to the back end. And so I mean, therein lies the architectural challenge. It's what data do we send to the back end? What data has utility in the back end for the great analytics that we're going to get by looking at the entire concept and sending back out to the edge for processing purposes versus just noise data, just data that we have to transact. So
I love
I would
that
say,
point, William,
yeah,
because then you're just focusing on being reasonably practicable, and like that's all we should do in data quality anyway.
yes, yeah, exactly. Exactly. And yes, are you going to do data quality of that data? Are you going to change that data? Oh, yeah, absolutely. Absolutely. If you see patterns that you want to update, I kind of alluded to that before.
Mhm. Excellent. Well, thank you very much, William, for this wonderful presentation. That's all we have time for. And thank you, chat, for asking so many questions and being so electric as usual. And yeah, thanks again. Any parting thoughts, William, before I hit the end button?
Have a great day, everyone.
Thanks.